For centuries, the cosmos was imagined as a serene, empty void, a vast, silent expanse where nothing truly existed between the glittering stars. We often picture astronauts floating in a complete absence of matter. This perception, while visually compelling, vastly oversimplifies the true nature of what lies beyond Earth's protective atmosphere. While incredibly sparse, the cosmic vacuum is far from truly empty. What we call a vacuum in space isn't an absolute void, but rather a state of extremely low pressure and particle density. Even in the emptiest regions between galaxies, there's still, on average, at least one atom per cubic centimeter. That's significantly more empty than anything we can achieve in a laboratory on Earth, but it's not strictly zero. This incredibly diffuse matter consists primarily of hydrogen and helium atoms, the leftover building blocks from the Big Bang, along with trace amounts of heavier elements ejected by ancient stars. These particles zip around at high speeds, contributing to what is known as the interstellar or intergalactic medium, but their immense separation defines the vacuum. The temperature of this cosmic vacuum is generally frigid, hovering just a few degrees above absolute zero, around 2.7 Kelvin, due to the pervasive cosmic microwave background radiation. However, localized regions, heated by stellar winds or active galactic nuclei, can reach millions of degrees, creating pockets of superheated, extremely thin plasma. The pressure in space is extraordinarily low, often measured in fractions of a nanobar. This nearly perfect vacuum is what makes space so dangerous for unprotected human exposure, causing fluids to boil and tissues to swell. It's a stark reminder of the immense difference between our atmospheric home and the harsh cosmos. On Earth, our best laboratory vacuums, used in semiconductor manufacturing or particle accelerators, can achieve pressures hundreds of millions of times higher than interstellar space. Yet, even these contain vast numbers of residual molecules compared to the near-perfect vacuum of the cosmos. Our empty chambers are dense by cosmic standards. True absolute emptiness, a perfect vacuum with literally no particles or energy fields, is theoretically impossible according to quantum mechanics. Even in the deepest void, quantum fluctuations continuously create and annihilate virtual particles for fleeting moments, an invisible bubbling of existence unique to the quantum realm. This near vacuum profoundly impacts interstellar travel. There's no air resistance to slow spacecraft, but the sparse particles still pose a long-term erosion risk, and the absence of conductive material makes heat dissipation challenging for probes generating their own warmth. It's an environment that presents unique engineering hurdles. From a microscopic perspective, the particles in deep space are so far apart that collisions are incredibly rare. They essentially travel in straight lines for millions of miles before encountering another atom or photon. This vast emptiness on the atomic scale allows for incredibly long mean-free paths. And importantly, it's this extreme sparseness that directly explains why space is silent. Sound, as we perceive it, requires a medium, vibrating particles, to propagate. Without that medium, there's simply nothing for sound waves to push against, ensuring a profound and absolute acoustical stillness throughout the cosmos, despite its hidden activity. Despite the general silence, space is not truly empty. It's often filled with the interstellar medium, or ism, a diffuse mixture of gas and dust that permeates galaxies. Though tenuous, this material makes up a significant fraction of a galaxy's mass and is crucial for stellar evolution, acting as the raw material for new stars and planets. The gas in the ism is predominantly hydrogen and helium, the lightest elements forged in the Big Bang. It exists in various states: cold, dense molecular clouds where atoms bind together, warmer, neutral atomic hydrogen, and hot, ionized plasma in regions near stars or supernova remnants. Each state plays a unique role. Interstellar dust, while only about 1% of the ISM's mass, is crucial. These are microscopic solid particles like soot or silicon-based grains, roughly the size of cigarette smoke particles. They originate from the outer layers of aging stars and supernovas, acting as catalysts for chemical reactions and shielding denser regions. These dust grains are vital because they absorb and scatter starlight, making distant objects appear dimmer or redder, a phenomenon called interstellar reddening. This absorption also re-radiates light in the infrared, allowing astronomers to map out hidden nebulae and molecular clouds invisible to optical telescopes. The ISM isn't static. It's constantly churned by stellar winds, supernova explosions, and galactic rotation. This dynamic movement creates intricate structures, from giant molecular clouds spanning hundreds of light years to wispy filaments and dense knots, all shaping the environment for future celestial birth and death. Far from being uniform, the ISM has distinct phases. There's the hot, diffuse intercloud medium, the warmer and denser neutral hydrogen clouds, and the very cold, very dense molecular clouds, which are the gravitational cradles of star formation. Each phase represents a different cosmic state of matter. Astronomers study the ISM primarily through spectroscopy, analyzing how light from distant stars is absorbed or emitted by the gas and dust along the line of sight. This allows them to deduce the composition, temperature, density, and velocity of these elusive cosmic ingredients. The ISM truly transforms what we picture as empty space. It's a dynamic, ever-changing ocean where cosmic elements mix, forming a diverse ecosystem of particles that are denser and more complex than the true intergalactic void. Without it, new stars simply wouldn't form. This cosmic fog isn't just a backdrop, it's an active participant in galactic evolution. It fuels star birth, but also scatters light that could reveal alien civilizations. It's a complex, living component of the universe, demonstrating that empty space is anything but a passive backdrop. While the interstellar medium creates the conditions for cosmic phenomena, it doesn't carry sound. Its particles are too sparse and too far apart to effectively transmit vibrations. So even though it's brimming with material, the vast distances between particles still ensures that it remains acoustically silent. Beyond gas and dust, space is constantly bombarded by cosmic rays, not rays of light, but incredibly high-energy subatomic particles. These relentless travelers, mostly protons and atomic nuclei, zipping through the cosmos at nearly the speed of light, are a pervasive yet invisible component of the space environment. These energetic particles originate from a variety of violent cosmic events. Low-energy cosmic rays come from our Sun, but the most powerful ones are thought to be accelerated by supernova explosions and the powerful magnetic fields around neutron stars and black holes. They are the universe's ultimate particle accelerators. When cosmic rays strike Earth's atmosphere, they collide with atomic nuclei, creating cascades of secondary particles that rain down on the surface. We are constantly immersed in this cosmic background radiation, a natural consequence of living on a planet within an active galaxy. Cosmic rays pose a significant challenge for space exploration, especially for human missions beyond Earth's protective magnetic field and atmosphere. Prolonged exposure can damage DNA, increase cancer risk, and lead to various health problems. Developing effective shielding is paramount for future deep space travel. While dangerous, cosmic rays are also incredibly valuable for fundamental physics. By studying their properties, their energy, composition, and direction of arrival, scientists can gain insights into the most extreme environments in the universe and the mechanisms that accelerate particles to such incredible speeds. They are also a cosmic anomaly. Much of their origin remains elusive. The highest energy cosmic rays have energies millions of times greater than those produced by the largest particle accelerators on Earth, and tracking their sources is incredibly difficult because magnetic fields bend their paths. Detection of cosmic rays is done by ground-based observatories and satellites. Ground detectors often use large tanks of water to observe the Cherenkov radiation emitted by secondary particles, while space-based instruments directly measure the incoming primary particles before they hit the atmosphere. Cosmic rays modify the interstellar medium by ionizing atoms, creating conditions for complex chemical reactions that wouldn't otherwise occur. They contribute to the diffuse glow seen in some nebulae and power the magnetic fields that crisscross galaxies, linking disparate cosmic phenomena. Without cosmic rays, our galaxy would be a very different place. Their constant bombardment helps to heat and ionize the interstellar gas, contributing to the overall energetic balance of the galactic ecosystem. They are a constant, energetic pulse within the cosmos. Despite their incredible energy and prevalence, cosmic rays do not carry sound. They are individual particles, not waves of pressure. Their interaction with matter can produce detectable electromagnetic signals, but these are distinct from sound waves, once again affirming the profound silence of space. While space is silent, it's not entirely unchanging. The very fabric of spacetime itself can be disturbed by the most energetic events in the universe, creating phenomena known as gravitational waves. These are ripples in the geometry of spacetime, traveling at the speed of light, carrying information directly about their catastrophic origins. Predicted by Albert Einstein's general theory of relativity over a century ago, gravitational waves are generated by accelerating masses, much like electromagnetic waves are generated by accelerating charges. However, only the most violent cosmic events involving colossal masses can produce detectable ripples. The most powerful sources of gravitational waves include the collision and merger of black holes, the spiraling embrace of neutron stars, and the explosive deaths of massive stars. These cataclysms warp spacetime so dramatically that even at cosmic distances, we can detect their faint echoes. When a gravitational wave passes through an object, it momentarily stretches and squeezes space in perpendicular directions. These distortions are incredibly tiny, far smaller than the diameter of a proton, making their detection an extraordinary technological feat, requiring exquisitely sensitive instruments. The first direct detection of gravitational waves in 2015 by the LIGO Observatory signaled a new era of astronomy. It confirmed Einstein's century-old prediction and allowed us to hear the universe in a completely new way, providing insights inaccessible with light alone. Gravitational wave astronomy offers a unique window into the dark side of the universe. Black holes and neutron stars emit no light, making them invisible to traditional telescopes. But their mergers emit powerful gravitational waves, allowing us to study these enigmatic objects directly. Unlike light, which can be absorbed or scattered by gas and dust, gravitational waves pass through matter unimpeded. This means they can carry information from the very heart of supernovae or from the earliest moments of the Big Bang, reaching us without distortion. Gravitational wave observatories like LIGO, Virgo, and KAGRA are continuously being upgraded, and future projects like the Laser Interferometer Space Antenna, LISA, will operate in space to detect much lower frequency waves, potentially from supermassive black hole mergers. The information carried by gravitational waves includes the masses of the merging objects, their spins, and their distance from Earth. Analyzing the subtle chirp sound reconstructed from these wave patterns allows astrophysicists to unravel the dynamics of these extreme cosmic collisions. While we describe gravitational waves as chirps or sounds, it's important to remember they are not sound in the traditional sense. They are distortions of spacetime detected by instruments and converted into audible frequencies for human interpretation. The universe remains profoundly silent to our ears. One of the most profound mysteries of the cosmos is dark matter. Despite its name, it's not dark as in black, but dark as in non-luminous, meaning it doesn't emit, absorb, or reflect light or any other form of electromagnetic radiation. It's completely invisible to our usual observational tools. The evidence for dark matter is overwhelming and comes primarily from its gravitational effects. Galaxies spin too fast for their visible matter to hold them together without flying apart. Galaxy clusters are too massive, and light bends around them far more than visible matter alone would permit. Dark matter accounts for approximately 27% of the universe's mass-energy budget, 4 times more than all the ordinary matter combined, the protons, neutrons, and electrons that make up everything we can see and touch. It's the dominant form of matter in the cosmos. Scientists believe dark matter forms vast cosmic scaffolds, creating the gravitational wells into which ordinary matter falls and clumps to form galaxies and galaxy clusters. Without dark matter, large-scale structures like galaxies might never have formed. What actually constitutes dark matter is still unknown, representing one of the greatest challenges in modern physics. Leading candidates include weakly interacting massive particles, or WIMPs, hypothetical particles that interact gravitationally but rarely with other forms of matter. Experiments worldwide are actively searching for dark matter. Underground laboratories use highly sensitive detectors, shielded from cosmic rays, hoping to observe a rare collision between a WIMP and an atomic nucleus, converting its energy into a detectable signal. While WIMPs are the primary target, other theories propose different cold dark matter candidates, like axions or sterile neutrinos, or even primordial black holes. The hunt for direct detection is complex, requiring innovative approaches and extreme precision. Dark matter doesn't clump neatly. It forms vast halos surrounding and permeating galaxies. Our own Milky Way is believed to be embedded within a massive, extended halo of dark matter that stretches far beyond its visible stellar disk. The Bullet Cluster provides compelling visual evidence for dark matter. This system of colliding galaxy clusters shows a clear separation between the hot X-ray emitting gas and the gravitational lensing effect, indicating that most of the mass is not in the visible gas. Despite its immense gravitational influence, dark matter is acoustically inert. It only interacts via gravity, meaning it doesn't collide or vibrate in a way that would generate or transmit sound waves. It contributes to the cosmic silence, a vast, invisible, and utterly quiet gravitational presence. Adding to the universe's mysterious composition is dark energy, an even more enigmatic entity than dark matter. It's not matter at all. Instead, it seems to be a strange, pervasive force intrinsic to space itself, responsible for the accelerating expansion of the universe. The discovery of accelerating expansion in the late 1990s was a monumental shock. Earlier, astronomers expected gravity to slow down expansion. But observations of distant supernovae showed them to be dimmer than expected, implying they were farther away, meaning the universe was expanding faster and faster. Dark energy makes up approximately 68% of the universe's total mass energy density, making it the most dominant component of our cosmos. Ordinary matter and dark matter combined only make up about 32%. We truly live in a universe dominated by the unknown. The most straightforward explanation for dark energy is it's the cosmological constant, a concept proposed by Einstein, but which he later called his biggest blunder. This constant represents the energy of empty space itself, exerting a repulsive gravitational force. If dark energy is indeed a cosmological constant, its density remains constant even as the universe expands, meaning its influence becomes proportionally greater over time. This leads to a future where galaxies beyond our local group recede faster than light, eventually becoming forever out of reach. Alternative theories for dark energy include evolving scalar fields or modifications to Einstein's theory of gravity itself. Researchers are actively pursuing multiple avenues to understand this mysterious force, as its nature will dictate the ultimate fate of the universe. Observations from missions like the Hubble Space Telescope and ground-based surveys like DAISY map out distant galaxies to precisely measure the expansion rate and its acceleration. These cosmic rulers help constrain the properties of dark energy. The immediate future of the universe is largely determined by dark energy. If it persists, our universe is headed for a big freeze or heat death, where galaxies become isolated islands, stars eventually die out, and the universe becomes cold, dark, and utterly vast. Dark energy defines the very large-scale structure and evolution of the universe. It's the engine driving the cosmos apart, an invisible, pervasive anti-gravity force that fundamentally changes our understanding of the universe's past, present, and far future. Like dark matter, dark energy is entirely non-interacting in ways that would produce sound. It's a property of space itself, a force, not a medium for vibrations. It orchestrates the silent, accelerating symphony of cosmic expansion, but its profound influence contributes no audible note to the universe. While much of space is empty, it's also teeming with countless worlds. Planets and moons, diverse in their composition and environment, are now known to be incredibly common throughout our galaxy and likely across the universe. Our solar system is just one example of this cosmic abundance. From scorching hot, lava worlds, orbiting close to their stars, to frozen, distant ice giants, exoplanets display an astonishing range of characteristics. Thousands have been confirmed, with millions more awaiting discovery, each a potential laboratory for unique geological and atmospheric processes. Our own solar system boasts 8 major planets and numerous dwarf planets. From the rocky inner worlds like Mars to the gas giants like Jupiter with its colossal storms, each has a distinct personality shaped by its distance from the Sun and its formation history. Moons are equally diverse, often revealing surprises. Jupiter's Europa, a potential ocean world beneath its icy crust, and Saturn's Titan, with its thick atmosphere and liquid methane lakes, are prime targets in the search for extraterrestrial life, demonstrating geological activity far from their star. Planetary formation begins in protoplanetary disks of gas and dust swirling around newborn stars. Over millions of years, tiny particles clump together through accretion, gradually forming planetesimals, then protoplanets, eventually sweeping up enough material to become full-fledged planets. The search for exoplanets uses various methods. The transit method observes tiny dips in a star's brightness as a planet passes in front of it. The radial velocity method detects the wobble in a star caused by a planet's gravitational pull. Each technique reveals different planetary characteristics. The concept of a habitable zone, or Goldilocks zone, defines the region around a star where temperatures might allow liquid water to exist on a planet's surface. This is a key criterion in the search for life as we know it, though exotic forms of life could exist elsewhere. Analyzing the atmospheres of exoplanets for biosignatures, chemical imbalances like large amounts of oxygen, is a frontier of astrobiology. Future telescopes will have the sensitivity to peer into these distant atmospheres, potentially revealing signs of life. The sheer number of planets suggests that habitable conditions might not be as rare as once thought, challenging our assumptions about unique Earth. While life remains undetected beyond Earth, the probability is increasing that it exists elsewhere, given the sheer number of worlds. While planets and moons offer surfaces where sound can travel, and some, like Earth, have atmospheres that permit it, the vast stretches of space between them are silent. Any sounds generated on these worlds are confined to their immediate vicinity, unable to cross the cosmic void. Stars are the fundamental building blocks of galaxies, colossal furnaces of plasma performing nuclear fusion. They illuminate the cosmos, produce the heavy elements essential for life, and drive the evolution of their surrounding environments, acting as cosmic powerhouses. Stellar nurseries, often nestled within giant molecular clouds, are where stars are born. Gravity pulls denser knots of gas and dust together, causing them to collapse and spin, eventually forming hot, dense protostars that ignite nuclear fusion in their cores. Stars come in an astonishing range of sizes, masses, and temperatures, from dimmer, cooler red dwarfs, which can live for trillions of years, to massive, hot, short-lived blue giants that burn brightly for only a few million years before exploding spectacularly. Each star type has a unique lifespan. Our Sun is a middle-aged, main-sequence star, roughly 4.6 billion years old. It converts hydrogen into helium in its core, releasing immense energy in the form of light and heat, sustaining life on Earth and defining our local cosmic environment. The life cycle of a star is a cosmic drama. After exhausting their hydrogen fuel, stars like the Sun expand into red giants, shed their outer layers as planetary nebulae, and eventually shrink to become white dwarfs. More massive stars end their lives as supernovae. Supernovae are among the most cataclysmic events in the universe. They are the explosive deaths of massive stars, briefly outshining entire galaxies. These explosions forge and disperse heavy elements like carbon, oxygen, and iron, crucial for planets and life. The remnants of supernovae can be neutron stars, incredibly dense objects composed almost entirely of neutrons, or, in the case of the most massive stars, black holes. These stellar corpses continue to influence their surroundings long after their fiery demise. Stellar winds, streams of charged particles constantly flowing from stars, interact with the interstellar medium, creating beautiful nebulae and shockwaves. These winds are crucial for shaping star-forming regions and distributing elements throughout the galaxy. The distribution of stars within a galaxy also tells a story. Older populations tend to reside in the central bulge and halo, while younger stars are found in the spiral arms, where fresh gas and dust are constantly collapsing to form new generations. While stars are sources of immense energy, their light and heat do not create sound in a vacuum. Sound can only travel through the plasma of the star itself. In the vast vacuum between stars, their brilliant fiery activity produces no audible noise, only silent, pervasive illumination. Galaxies are the grand architectures of the cosmos, colossal island universes containing billions, sometimes trillions, of stars, along with vast quantities of gas, dust, dark matter, and dark energy. They are the fundamental, large-scale structures of the visible universe. Galaxies come in various types. Spiral galaxies, like our Milky Way, feature prominent rotating arms. Elliptical galaxies are smooth, featureless spheres or ovals, typically composed of older stars. Irregular galaxies lack a definite structure, often resulting from galactic collisions. Our own Milky Way is a barred spiral galaxy, a magnificent flattened disk spanning about 100,000 light-years, containing estimations of 200 to 400 billion stars. The Sun resides in one of its minor spiral arms, about two-thirds of the way out from the galactic center. At the heart of most large galaxies, including our own, lies a supermassive black hole, weighing millions to billions of times the mass of the Sun. These colossal objects profoundly influence the dynamics and evolution of their host galaxies, even though they are invisible themselves. Galaxies are not solitary. They often cluster together in groups and superclusters bound by gravity. Our Milky Way is part of the local group, which also includes the Andromeda Galaxy and dozens of smaller dwarf galaxies, all drawing closer to each other. Galactic collisions, though seemingly catastrophic, are more like slow dances. Stars rarely collide due to the vast distances between them. Instead, galaxies warp, merge, and reform over millions of years, triggering bursts of star formation and reshaping cosmic structures. Active galactic nuclei, or AGNs, are extremely luminous centers of some galaxies, powered by supermassive black holes accreting vast amounts of matter. These AGNs can outshine the entire galaxy and drive powerful jets of radiation far into intergalactic space. The first galaxies began forming hundreds of millions of years after the Big Bang, starting from small clumps of dark matter and primordial gas. Over cosmic time, these initial structures merged and grew, building up the rich tapestry of galaxies we observe today. Studying galaxies provides insights into cosmic evolution, the distribution of matter, and the role of dark matter and dark energy on the grandest scales. They are the cosmic laboratories where processes of star formation, mergers, and black hole growth unfold. While galaxies are vibrant with stellar activity and gravitational interactions, their sheer distances and the vacuum between them ensure their collective silence. The immense cosmic forces at play within them do not translate into audible phenomena across the vast interstellar and intergalactic voids. Black holes are among the most enigmatic and extreme objects in the universe. They are regions of spacetime where gravity is so intense that nothing, not even light, can escape. They arise from the catastrophic collapse of massive stars or by the merger of immense cosmic structures. The boundary beyond which escape is impossible is called the event horizon. Crossing it means being inevitably pulled towards the singularity at the black hole's center, a point of infinite density where the laws of physics, as we know them, break down. Black holes come in different sizes. Stellar mass black holes, created from the collapse of individual massive stars, typically range from a few to tens of solar masses. Supermassive black holes, found at galaxy centers, can contain millions or even billions of solar masses. Though dark themselves, black holes are often detectable by their effects on surrounding matter. Accretion disks of gas and dust spiraling into a black hole heat up to incredible temperatures, emitting powerful X-rays and gamma rays that astronomers can observe. The gravitational influence of black holes extends far beyond their event horizons. They govern the orbits of stars in their vicinity, pulling them in extreme trajectories and causing them to accelerate to immense speeds, providing indirect evidence of their presence. Supermassive black holes play a crucial, if sometimes controversial, role in galaxy evolution. Their powerful jets and radiation can influence star formation in the host galaxy, either stimulating or suppressing it, depending on the energy output. The first image of a black hole's shadow, captured by the Event Horizon Telescope in 2019, was a monumental achievement. It revealed the silhouette of the supermassive black hole at the center of the galaxy M87, providing direct visual confirmation of these elusive objects. Black holes don't suck everything in. Matter typically has to be on a precise trajectory to fall in. Stars can orbit black holes safely for billions of years, just as planets orbit a star. Only if matter gets too close, past the event horizon, is it truly doomed. Stephen Hawking's theory of Hawking radiation suggests that black holes are not entirely black. They slowly lose mass over incredibly long timescales by emitting a faint thermal radiation, implying they eventually evaporate, though this process is too slow to observe for known black holes. Despite their immense power and gravitational influence, black holes are silent. They do not produce sound. Any sounds we associate with them, such as the chirp of merging black holes from gravitational waves, are translated data. In their cosmic realm, these giants are profoundly quiet. The fundamental reason space is silent lies in the very nature of sound itself. Sound is a mechanical wave, meaning it requires a medium, a collection of particles through which to propagate. It travels by causing these particles to vibrate and collide with their neighbors, transmitting energy. Imagine throwing a pebble into a still pond. The ripples spread because water molecules push against each other. Sound works similarly in air, water, or solids. The vibrations physically compress and expand the medium, carrying the waves. In a vacuum of space, however, there are simply not enough particles close enough together for these vibrations to transmit effectively. The immense distances between individual atoms or molecules mean collisions are too infrequent to carry a coherent wave. The density of air at sea level on Earth is about 1019 molecules per cubic centimeter. In interstellar space, that density drops to roughly 1 atom per cubic centimeter, a difference of 19 orders of magnitude. This dramatic reduction is key to the silence. Even if an incredibly loud explosion were to occur in space, like a supernova, the shockwave of expanding plasma would still not produce sound that could be heard from afar. The particles in that shockwave would simply expand into the void without a medium to transmit their vibrations. While the interstellar medium contains gas and dust, it's still too diffuse for sound. The particles are too far apart to effectively bump into each other and transmit a pressure wave over any significant distance. The effective mean-free path is enormous. The concept of listening to space using radio waves or other electromagnetic radiation is a completely different process. These are not mechanical waves and do not require a medium. They can travel perfectly well through a vacuum at the speed of light. Astronauts in space cannot hear each other directly without radios. Their helmets and spacecraft serve as terrestrial environments containing air. Outside, their walkie-talkies rely on radio waves, not sound waves, for communication. If a human was somehow exposed to the vacuum of space without protection, their body fluids would boil and they would suffocate due to lack of oxygen, but they wouldn't hear anything. The last sensation would be the excruciating pressure of their own body. So the silence of space is not a poetic abstraction, but a direct consequence of fundamental physics. It's a literal emptiness from an acoustical perspective, reinforcing our unique position on a planet with a life-sustaining atmosphere that allows for the very existence of sound. When sound is absent from space, our primary means of observation and communication across the cosmos is through the electromagnetic spectrum. This vast range of energy includes everything from radio waves and microwaves to infrared, visible light, ultraviolet, X-rays, and gamma rays. Unlike sound, electromagnetic waves do not require a medium to travel. They are self-propagating vibrations of electric and magnetic fields, effortlessly traversing the vacuum of space at the speed of light, carrying immense amounts of information about distant objects. Each part of the spectrum reveals different aspects of the universe. Radio waves penetrate gas and dust, showing cold, neutral hydrogen. Infrared light pierces dust clouds, revealing star formation. Visible light shows stars and galaxies. Ultraviolet radiation exposes hot, young stars and active galactic nuclei. X-rays reveal high-energy phenomena like supernova remnants, black holes, and galaxy clusters. Gamma rays, the most energetic, originate from the most violent cosmic events, such as gamma-ray bursts. Earth's atmosphere selectively blocks much of the electromagnetic spectrum, absorbing harmful high-energy radiation like X-rays and gamma rays, protecting life. This is why many telescopes, particularly those observing these wavelengths, must be launched into space. Astronomers use incredibly specialized telescopes to capture these different wavelengths. Radio observatories feature massive dishes, while X-ray telescopes use grazing incidence mirrors to focus the high-energy photons. Each instrument is perfectly tuned for its cosmic signal. Multi-messenger astronomy, combining observations from different parts of the electromagnetic spectrum with gravitational waves or neutrinos, is revolutionizing our understanding of cosmic events. It paints a more complete picture, transcending individual forms of data. The electromagnetic spectrum allows us to remotely sense the universe. We can determine the composition, temperature, velocity, and distance of objects by analyzing their unique spectral fingerprints. Each atom and molecule emits or absorbs at specific wavelengths. This spectrum is not merely a tool for observation, it's the very medium of information exchange throughout the universe. From quasar light to cosmic microwave background, every signal paints a part of the universe's grand narrative. Without the ability of electromagnetic waves to travel through the absolute silence of space, our knowledge of the cosmos would be devastatingly limited. It's our cosmic language, allowing us to see and read the universe, compensating for its profound, enveloping silence. Among the most powerful tools in our exploration of the cosmos is radio astronomy. Instead of visible light, radio telescopes detect radio waves, the longest wavelengths on the electromagnetic spectrum. These waves offer a unique window into objects that are otherwise invisible. Radio waves are particularly useful because they can penetrate vast clouds of gas and dust that would block visible light, allowing us to peer into the heart of dusty galaxies, dense star-forming regions, and the mysterious galactic center, revealing hidden structures. Many cosmic objects emit strongly in radio wavelengths. Cold hydrogen gas, for instance, emits a characteristic 21-centimeter radio line, allowing astronomers to map the spiral arms of our galaxy and study gas distribution across vast cosmic distances. Pulsars, rapidly spinning neutron stars, emit beams of radio waves that sweep across Earth, creating regular pulses much like a lighthouse. These incredibly precise cosmic clocks are discovered and studied primarily through radio astronomy. Quasars, the extremely luminous cores of distant galaxies powered by supermassive black holes, are also strong radio sources. These cosmic beacons, often billions of light years away, allow us to probe the early universe and galactic evolution. Radio astronomy has revolutionized our understanding of the universe. Discoveries such as the cosmic microwave background radiation, the faint afterglow of the Big Bang, were made using radio telescopes, providing crucial evidence for the universe's origin. Large arrays of radio telescopes, like the Very Large Array in New Mexico, combine signals from multiple dishes to create a single, much larger virtual telescope. This technique, called interferometry, dramatically improves resolution and sensitivity. Radio telescopes are crucial for studies of interstellar molecules. They detect the unique radio fingerprints of molecules in dense clouds, revealing the complex chemistry occurring in star-forming regions and hinting at building blocks for life. The atmosphere is mostly transparent to radio waves, allowing ground-based radio observatories to operate continuously, unlike optical telescopes, which are hampered by clouds and daylight. This makes radio astronomy a powerful round-the-clock observational tool. While we listen to the universe with radio telescopes, it's vital to remember that we aren't hearing sound. We are detecting electromagnetic radiation, which our instruments convert into signals we can process. The cosmos remains acoustically profoundly silent. One of the most fundamental constants in the universe and a profound limiter of our observations is the speed of light. Light travels at approximately 300,000 kilometers per second in a vacuum, the fastest anything can possibly move. This cosmic speed limit governs everything we see. The finite speed of light means that when we look out into space, we are inherently looking back in time. The light from distant galaxies takes billions of years to reach us, so we see them as they were, not as they are now. The farther we look, the further back in time we see. For example, light from the nearest star, Proxima Centauri, takes just over 4 years to reach Earth. If it were to suddenly vanish, we wouldn't know for over 4 years. This inherent time delay affects all our observations across the universe. This cosmic time machine allows us to study the evolution of galaxies and the universe itself. We can observe different epochs of cosmic history by simply observing objects at increasing distances, effectively seeing snapshots of the universe at various stages of its development. Understanding the speed of light is crucial for accurate distance measurements in astronomy. Techniques like standard candles, such as Type Ia supernovae, rely on their known intrinsic brightness to calculate distances based on how dim they appear, accounting for light travel time. The concept of the observable universe is directly a result of the speed of light and the universe's age. We can only see light from regions from which light has had enough time to reach us since the Big Bang, creating a theoretical boundary to our cosmic view. For potential extraterrestrial civilizations, the speed of light is both a blessing and a curse. It ensures their signals arrive clearly through the vacuum, but it also imposes immense communication delays, making any meaningful conversation across interstellar distances incredibly challenging. Looking at the sun, we are seeing it as it was 8 minutes ago. When you look at the moon, you're seeing it as it was about 1¼ seconds ago. These seemingly instantaneous views are, in fact, always glimpses into the immediate past. Without the constant speed of light, our universe would be chaotic and incomprehensible. It underlies fundamental physical laws, from relativity to electromagnetism, creating the predictable cosmic stage upon which everything unfolds, including the silent vacuum. The speed of light means that any sound or vibration originating from a cosmic event would simply have no way to reach us across the vast distances of empty space. We only receive its visual or electromagnetic signature, translated from light years into light seconds as it arrives. One of the most profound discoveries of the 20th century was that the universe is not static, it is expanding. All galaxies, on average, are moving away from each other. This cosmic expansion, first observed by Edwin Hubble, is a fundamental property of spacetime itself. The primary evidence for this expansion comes from the phenomenon of redshift. As light from distant galaxies travels through expanding space, its wavelength is stretched, shifting it towards the red end of the spectrum, similar to the Doppler effect for sound. Just as an ambulance siren sounds lower in pitch as it moves away, light waves from receding galaxies appear redder. The greater the redshift, the faster the galaxy is receding, and by Hubble's law, the farther away it is, confirming the constant expansion. Hubble's law states that a galaxy's recessional velocity is directly proportional to its distance from us. This relationship provides a crucial method for determining cosmic distances, extending our reach far beyond standard candles. The expansion is not an explosion outwards from a central point. Instead, space itself is stretching, carrying the galaxies along with it. Every point in the universe can be considered the center of the expansion, as all observable galaxies are receding from each other. Cosmic microwave background, the oldest light in the universe, is heavily redshifted into the microwave range, a testament to the immense stretching of space since the Big Bang. This ancient light confirms the universe's hot, dense beginning. Measuring redshift precisely is vital for cosmological models. It allows scientists to probe the universe's past expansion rate and understand the effects of dark matter and dark energy, which are key drivers of cosmic evolution. The expansion of the universe also affects the detectability of signals. As space stretches, so do the wavelengths of any signals traveling through it, making very distant light incredibly dim and redshifted, eventually shifting it completely out of our observational window. While the expansion happens everywhere, local gravitational forces can counteract it. Our Milky Way and Andromeda galaxies are gravitationally bound within the local group and are actually moving towards each other, destined to merge in billions of years. The expanding universe, with its redshifted light, tells a silent story of creation, growth, and the future. This dynamic, vast process, measurable through light, once again operates without any audible component, ensuring the profound quietness of the cosmos despite its grand scale. Within the vast silence of space, there is a symphony of cosmic noise, not audible sound, but a cacophony of electromagnetic radiation generated by powerful natural phenomena. These signals, when detected by our instruments, are translated into data that reveal the universe's hidden activity. Pulsars, rapidly spinning neutron stars, emit incredibly precise periodic bursts of radio waves. These highly regular signals were initially mistaken for artificial beacons, leading to their whimsical nickname, LGM-1, Little Green Men. Quasars, the brilliant cores of active galaxies, some billions of light-years away, are among the most luminous objects in the universe, radiating across the entire electromagnetic spectrum, particularly in radio waves and X-rays. They are like cosmic lighthouses. These energetic signals are not random noise. They carry specific information, the precise timing of a pulsar's spin, the spectral lines revealing a quasar's composition and enormous redshift. By analyzing these cosmic messages, we learn about extreme physics. The cosmic microwave background, or CMB, is the most pervasive and ancient noise in the universe. It's the faint afterglow of the Big Bang, a uniform bath of microwave radiation that permeates all of space, providing a snapshot of the young universe. The discovery of the CMB in 1964 was accidental. Arno Penzias and Robert Wilson, while testing a new horn antenna, consistently detected a persistent, annoying hiss that came from all directions and could not be removed. They had found the Big Bang's relic. Beyond these, other cosmic noise includes fast radio bursts, FRBs, extremely powerful but very short bursts of radio energy from unknown origins, and the diffuse X-ray background from countless unresolved distant objects. The cosmic whisper of gravitational waves, as detected by LIGO, is yet another form of noise, translated into an audible chirp. While not sound, it's a direct ripple in spacetime, a different channel for information about extreme cosmic events like black hole mergers. These natural sources of radiation are immensely powerful. A single gamma-ray burst can release more energy than the Sun will in its entire 10 billion-year lifetime, making them the most luminous events in the universe since the Big Bang. So while space is acoustically silent, it's far from quiet to our instruments. It pulses with light, radio waves, X-rays, and even gravitational ripples, a constant cosmic symphony of non-audible information waiting to be detected and interpreted. Amidst the natural cosmic signals, humanity has long wondered, are there other intelligent civilizations out there? This profound question drives the search for extraterrestrial intelligence, or SETI, an ongoing scientific endeavor to detect signs of life beyond Earth. The primary strategy of SETI involves listening for artificial signals, typically in the radio portion of the electromagnetic spectrum. Radio waves are chosen because they travel unimpeded through space and are relatively easy to generate and detect over vast distances. Early SETI experiments, like Project Ozma in 1960, focused on a few nearby stars. Today, large surveys like Breakthrough Listen use powerful telescopes to scan millions of star systems, searching for non-natural, narrowband, or pulsed signals. WOW signal, a strong, narrowband radio signal detected in 1977 by the Big Ear Radio Telescope, remains one of the most intriguing yet unconfirmed SETI detections. It lasted 72 seconds and perfectly matched expectations for an artificial, non-terrestrial signal. SETI isn't just about passive listening. Active SETI, or METI, messaging extraterrestrial intelligence, involves deliberately sending messages from Earth into space, a controversial approach due to the unknown nature of potential recipients. The search extends beyond radio. Researchers are now also looking for optical signals, such as laser pulses and even technosignatures, any signs of technology that might be observable across interstellar distances, like artificial megastructures. The sheer volume of cosmic noise can overwhelm faint artificial signals. Sophisticated algorithms and powerful computing are essential to filter out natural astrophysical phenomena and identify any true anomalies that might point to intelligent origins. International cooperation is fundamental to SETI. Data is often shared and analyzed by a global network of researchers, ensuring broad scrutiny and avoiding misinterpretations. This collective effort epitomizes humanity's shared cosmic curiosity. Even without a detection, the process of SETI is scientifically valuable. It pushes the boundaries of observational astronomy, develops new signal processing techniques, and forces us to confront fundamental questions about life, intelligence, and our place in the universe. SETI operates in a cosmos that is acoustically silent, transforming faint electromagnetic whispers into meaningful data. Any signal, if found, would be processed soundlessly by our machines, revealing its intelligence without ever breaking the universe's pervasive and fundamental quiet. Beyond deliberate communication signals, an increasingly broad approach in SETI involves searching for technosignatures, any detectable indicators of technology used by an extraterrestrial civilization. These are measurable characteristics that are highly unlikely to arise from natural astrophysical processes. One proposed technosignature is the presence of megastructures, like a Dyson sphere or swarm, designed to capture a star's energy. Such a structure would significantly alter a star's observable light, possibly obscuring it or causing unusual dimming patterns. Industrial pollution in an exoplanet atmosphere could also be a technosignature. Detecting unusual chemical compounds, like chlorofluorocarbons, that are not produced naturally could indicate an advanced industrial society. Non-natural radio or laser emissions are the classic technosignature. Unlike a pulsar's broadband emissions, an artificial signal might be incredibly narrowband, pulsed, or exhibit complex modulations indicative of intelligence, standing out from cosmic noise. The waste heat from super-advanced civilizations, if they consume vast amounts of energy, might be detectable as unusually high infrared emissions from star systems. Such an excess of infrared could be a subtle sign of energy harvesting. Evidence of planetary engineering, such as artificial structures on a planet's surface or alterations to its orbit, could theoretically be discernible with future, incredibly powerful telescopes. These are high-level signatures far beyond current capabilities. The search for technosignatures is inherently speculative. We don't know what advanced civilizations might build or how they would use energy. This requires an open mind and a willingness to look for the truly unexpected within our cosmic data. The key challenge is distinguishing true technosignatures from natural astrophysical phenomena that might mimic them. This demands a deep understanding of cosmology, astrophysics, and extremely rigorous data analysis to avoid false positives. Technosignatures could represent a passive form of contact, revealing the presence of intelligence without intentional communication. This could be our most likely path to discovery, as deliberate signals might be rare or directed elsewhere. In the realm of technosignatures, artificiality and order are key. Even in the profound silence of space, geometry, unusual energy consumption, or highly precise, non-random signals would be the silent flags of a distant civilization, waiting for our instruments to perceive them. If life is common in the universe, and advanced civilizations are capable of interstellar travel or communication, then why haven't we detected any evidence of them? This profound contradiction is known as the Fermi paradox, a central dilemma in astrobiology. The universe is ancient and vast. If even a small fraction of civilizations developed and colonized a galaxy, they should have done so over billions of years, spreading across vast distances, potentially reaching every star system. The paradox, first articulated by physicist Enrico Fermi, highlights the stark contrast between the high probability of extraterrestrial intelligence, given the vast number of stars and planets, and the utter lack of any observable evidence. One category of solutions suggests that extraterrestrial intelligence is, in fact, rare. Perhaps the conditions for life to arise are extremely specific, or the pathway from simple life to complex, intelligent, and spacefaring civilizations is incredibly improbable. Another set of solutions posits that intelligence, even if common, might not last long. Civilizations might self-destruct through war, environmental collapse, or technological mishaps before they can become interstellar. This is known as the Great Filter. There's also the possibility that they are out there, but we simply haven't found them yet due to technological limitations, vast distances, or because their signals are too faint or don't match our assumptions of what intelligence would look like. Or perhaps advanced civilizations aren't interested in communicating with us or are deliberately hiding. Some theories suggest a zoo hypothesis, where Earth is a protected preserve, or a dark forest theory, where silence is maintained for survival. They might also simply be too alien to recognize. Their technology, biology, or communication methods could be utterly beyond our current comprehension, making any signals or technosignatures invisible or meaningless to our instruments and minds. The ultimate implications of the Fermi paradox are profound. If we are truly alone, it places an immense responsibility on humanity to preserve life. If not, it means an incredible discovery awaits, challenging our entire worldview. The silence of the universe, therefore, isn't just a physical phenomenon, it's a philosophical one. It amplifies the Fermi paradox, turning the quiet hum of the cosmos into a tantalizing, yet frustrating question mark about our place in the cosmic tapestry. To address the Fermi paradox and estimate the number of detectable civilizations in our galaxy, astronomer Frank Drake formulated his famous Drake equation in 1961. It's a probabilistic framework, not a definitive calculation, designed to stimulate scientific discussion. The Drake equation multiplies several factors together: the rate of star formation, the fraction of stars with planets, the average number of habitable planets per star, the fraction of those where life arises, and the fraction where intelligent life develops. It then considers the fraction of intelligent civilizations that develop technology capable of interstellar communication. And finally, the length of time such civilizations release detectable signals into space. Each factor introduces significant uncertainty. N equals R times Fp times Ni times Fl times Phi times Fc times Ln is the number of civilizations we might detect. R is the rate of star formation. Fp is the fraction of stars with planets. Ni is the average number of planets per star that can support life. Then Fl is the fraction of life-supporting planets where life actually emerges. Phi is the fraction of those where intelligent life evolves. Fc is the fraction of those that develop detectable communication technology. And finally, L, perhaps the most critical and uncertain factor, is the length of time such civilizations release detectable signals into space. This factor strongly influences the final number and plays a key role in the Fermi paradox. Frank Drake himself estimated n to be around 10, meaning perhaps 10 civilizations in the Milky Way today. However, even slight changes in the estimated values for each factor can lead to answers ranging from 1 us to millions. The immense uncertainties, especially for FL, phi, and L, make the Drake equation more of a philosophical tool and a research agenda than a precise calculation. It highlights what we need to learn to answer the question of life in the universe. Recent exoplanet discoveries have boosted the values for R and FP significantly. We now know that planets are incredibly common, but the later biological and sociological factors remain highly speculative and are the true bottleneck. The Drake equation implicitly underscores the silence of space. If that final L factor is very short due to self-destruction or other filters, then the galaxy could be filled with the silent remnants of civilizations, never having achieved detectable longevity. Astrobiology, the study of life in the universe, grapples with a fundamental question: is life rare or common? This field combines biology, astronomy, geology, and chemistry to understand the origins, evolution, distribution, and future of life. The question of abiogenesis, how life arises from non-living matter, is central. On Earth, complex organic molecules, even amino acids, form naturally in diverse environments. But the step from these building blocks to self-replicating life remains largely mysterious. The RNA world hypothesis suggests that RNA, not DNA, was the primary genetic material in early life, performing both information storage and catalytic functions. This simplified genetic system may have been easier to spontaneously generate. For complex multicellular life, the Cambrian explosion on Earth signifies a rapid diversification of animal forms. This event, roughly 540 million years ago, suggests that even once life arises, the path to complexity might not be direct or inevitable. The energy source for life is also a key factor. While photosynthesis on Earth uses sunlight, chemosynthesis, found around hydrothermal vents, proves that life can thrive in the absence of light, sustained by chemical energy. This broadens the scope for life elsewhere. Extremophiles, organisms that thrive in extreme conditions on Earth, from boiling acid to frozen ice or intense radiation, demonstrate life's remarkable resilience and adaptability, suggesting that life could survive in surprisingly harsh exoplanetary environments. The very long period before complex life emerged on Earth, nearly 3 billion years after single-celled life arose, implies that even if simple life is common, the evolution of complex, let alone intelligent, life might be a very protracted and rare process. The question of whether intelligence is an inevitable evolutionary outcome or a felicitous accident is crucial. Many successful species on Earth, like insects, have thrived for hundreds of millions of years without developing technological intelligence. The presence of water, a suitable energy source, and stable environmental conditions are generally considered vital for life as we know it. The search for these conditions on exoplanets guides astrobiological missions and observations. Ultimately, the rarity or commonality of life remains an open question, amplified by the silent universe. If life is rare, then the cosmic silence is simply emptiness. If it is common, then the silence becomes a profound mystery, urging further exploration. The rare Earth hypothesis suggests that the combination of astrophysical and geological events needed to produce complex, intelligent life is exceedingly rare, making Earth a uniquely special or even singular abode for advanced life in the universe. One factor is our galaxy's habitable zone. We're not too close to the chaotic galactic center with its high radiation and frequent supernovae, nor too far out where heavy elements needed for planets are scarce. We're in a cosmic sweet spot. The Sun's stability is also crucial. It's a main sequence star, burning steadily for billions of years, avoiding the extreme variability of many other star types. This long, stable energy supply has been essential for Earth's evolution of complex life. The presence of Jupiter, our gas giant neighbor, acts as a cosmic vacuum cleaner, protecting Earth from frequent, devastating asteroid and comet impacts that could otherwise sterilize the planet, allowing life time to evolve. Earth's relatively large moon stabilizes its axial tilt, preventing extreme climate swings that would make long-term evolution of complex life very difficult. Without the moon, Earth's tilt would wobble chaotically, leading to radical temperature shifts. Plate tectonics, unique to Earth among solar system rocky planets, is considered vital. It drives the carbon-silicate cycle, regulating Earth's climate over geological timescales, creates vital geological diversity, and introduces new chemicals from the interior. The formation of the specific elements required for life, like carbon, oxygen, and iron, needs previous generations of massive stars to live and die in supernovae, enriching the interstellar medium into which our solar system formed. The precise timing of the evolution of life is also critical. If the Earth had formed too early or too late in cosmic history, it wouldn't have had the right elemental composition or the long-term stellar stability necessary for complex life. While compelling, the rare Earth hypothesis is debated. Critics argue that our understanding of planetary conditions and the pathways to life is still too limited to make such definitive conclusions about uniqueness. If the rare Earth hypothesis is true, then the cosmic silence takes on a lonely and profound meaning. It suggests that highly advanced life, capable of interstellar communication, might indeed be exceptionally rare, making our presence here all the more precious, isolated by silence. The emergence of complex, intelligent life is a story of biological evolution, a process driven by natural selection acting on genetic variation. On Earth, this pathway involves billions of years of adaptation and diversification, posing fundamental questions for astrobiology. The jump from simple prokaryotic cells, which dominated Earth for billions of years, to complex eukaryotic cells with specialized internal structures was a momentous evolutionary bottleneck. This endosymbiotic event was crucial for multicellularity. The evolution of multicellularity itself was another major hurdle, requiring cells to cooperate, specialize, and form complex tissues and organs. This was not a single event, but occurred multiple times in different lineages. Sexual reproduction, by shuffling genetic material, accelerates evolution and introduces new variations. While critical for Earth's biodiversity, its emergence and necessity vary, and alien life might evolve equally effectively through other reproductive means. The development of sensory organs, like eyes or ears, profoundly changed how life interacts with its environment. Different sensory modalities on alien worlds could lead to vastly different forms of intelligence and communication, perhaps based on something other than light or sound. The emergence of intelligence, particularly problem-solving abilities and complex communication, is perhaps the biggest constraint. On Earth, it evolved in specific lineages and is not necessarily an inevitable endpoint of evolution, even under favorable conditions. The evolution of tool use beyond simple manipulation, leading to complex technology, represents another major transition. This requires fine motor skills, abstract thought, and learning capacity, further narrowing the possible pathways to technological civilization. Environmental factors play a huge role. Mass extinctions, driven by natural catastrophes, periodically reset the evolutionary clock, allowing new forms of life to emerge and diversify, but also posing a constant threat to long-term stability. The question remains, are the pathways Earth took unique, Or are there convergent evolutionary pressures that would lead to similar outcomes elsewhere? Would intelligence, problem-solving, and communication invariably emerge given enough time? Ultimately, the slow, complex, and contingent march of biological evolution on Earth adds another layer to the cosmic silence. If the steps to intelligence are too numerous or fragile, the galaxy may be filled with silent, microbial worlds, forever unaware of each other. The Great Filter is a compelling solution to the Fermi paradox. It posits that at least one highly improbable, difficult, or even impossible step exists along the evolutionary path from the very beginning of life to an advanced, interstellar traveling civilization. This filter could be in our past. Perhaps the origin of life itself, abiogenesis, is fantastically rare. Or the evolution of complex, multicellular life, or the development of intelligent, tool-using brains could be the bottleneck. If the filter is in our past, it means humanity is incredibly special, having already overcome the most difficult hurdles. This would explain the silence. No one else made it this far, or their journey was so unique we simply don't see signs. Alternatively, the Great Filter could be in our future. This would imply that civilizations commonly arise and achieve advanced technology, but there's a catastrophic barrier they inevitably encounter before achieving interstellar colonization or long-term communication. Potential future filters include self-destruction through nuclear war, environmental collapse, uncontrolled artificial intelligence, resource depletion, or even some unknown, inevitable cosmic catastrophe. The existence of the Great Filter implies a daunting choice for humanity. Either we are exceptionally rare, having passed the filter, or it still lies ahead, a looming threat to our long-term survival that may explain the cosmic silence by explaining the absence of others. If the Great Filter is indeed in our future, then every observation suggesting life is common elsewhere becomes increasingly alarming. More life means more opportunities for civilizations to hit the filter before becoming detectable. Some argue that the very fact we are discussing the Great Filter and actively searching for extraterrestrial intelligence implies we haven't hit it yet. If it was a common, insurmountable bottleneck, we wouldn't exist to ponder it. Paradoxically, the discovery of even simple extraterrestrial life, like microbes on Mars or Europa, could be a terrifying revelation. It would suggest that either the abiogenesis filter is easily passed, pushing the Great Filter closer to our future. The Great Filter reinforces the profound silence of space. It's either the quiet of absence, because no one made it through, or the foreboding quiet of potential widespread self-destruction. The cosmic silence whispers a warning, whether it's from our past or our future. Many proposed Great Filter scenarios involve societal self-destruction. The history of humanity, coupled with the immense destructive power we've developed, suggests that advanced civilizations might inherently carry the seeds of their own demise, a universal threat. Nuclear warfare is a stark, immediate threat. The development of weapons of mass destruction, capable of rendering a planet uninhabitable, presents a clear, self-inflicted bottleneck for any technological civilization once it achieves atomic power. Environmental collapse, driven by uncontrolled industrial growth, resource depletion, climate change, or pollution, is another significant risk. A civilization might inadvertently destroy the very biosphere that sustains it. The rise of super-intelligent artificial intelligence could also pose an existential risk. If not properly controlled, an AI might act in ways detrimental to its creators, either deliberately or through unintended consequences of its goal optimization. Pandemics, both natural and engineered, could wipe out vast populations or even complete species before they can achieve interstellar capabilities. This biological barrier could be a powerful, silent filter. Resource scarcity and the ensuing conflicts could prevent sustained technological growth needed for interstellar expansion. Civilizations might exhaust essential materials on their home worlds, leading to internal strife or collapse. Societal stagnation or loss of curiosity might also be a filter. A civilization might reach a point where it loses the drive for exploration or innovation, becoming insular and eventually fading without reaching a detectable stage. The transition to multiplanetary species could be an insurmountable hurdle. Even if a civilization survives global threats, the challenge of building sustainable off-world colonies might be too great for species after species. Whether these threats are universal or specific to Earth-like civilizations is unknown. But if similar pressures exist across the cosmos, they could explain why the galaxy isn't teeming with radio signals. These self-destruction scenarios paint a grim picture, yet they serve as a powerful warning. The cosmic silence, in this context, is not just a physical property, but a potential echo of universal tragedies, a quiet graveyard of civilizations that couldn't overcome their inner demons. Another category of solutions to the Fermi paradox suggests that alien civilizations don't communicate with us because they are deliberately hiding or choosing not to reveal their presence. This concept introduces fascinating, if ominous, implications. The zoo hypothesis posits that Earth is a protected preserve, like a cosmic zoo or nature reserve. Advanced extraterrestrials are aware of us, but choose not to interfere, allowing our civilization to develop naturally, perhaps for scientific study or ethical reasons. Interference, according to this hypothesis, would contaminate our natural evolution or lead to unpredictable outcomes. They might adhere to a prime directive, a non-interference policy, similar to fictional ethical guidelines. Critiques of the zoo hypothesis point out its difficulty. It would require a uniform, galaxy-wide policy of non-interference maintained by all advanced civilizations over vast timescales, which seems unlikely given potential diversity. The dark forest hypothesis offers a more chilling explanation. It suggests that the universe is a dangerous place, a dark forest, where civilizations must remain utterly silent to avoid detection. Any signal reveals your presence, potentially inviting annihilation from more powerful or hostile civilizations. In this grim scenario, every civilization is a potential hunter or prey. The best way to survive is to be silent or to strike first if you detect another. Proactive communication becomes an existential risk, leading to universal quiet. The concept stems from a thought experiment based on the ruthlessness of survival. Resources are finite, and fear of competition or malice leads to preemptive elimination. This explains both the silence and the lack of colonization. If the dark forest theory is true, then humanity's active SETI efforts and outward messaging are incredibly dangerous, advertising our location and existence to potentially hostile entities. This raises profound ethical dilemmas about future contact. Both the zoo and dark forest hypotheses imply a universe filled with life and intelligence, but for vastly different reasons, it chooses to remain silent to us. The silence is not an absence, but a deliberate choice. The silence, therefore, continues to be a central puzzle. Is it the quiet of a watchful, benevolent guardian, or the eerie stillness of a cosmic ambush? Both scenarios make the universe's ultimate quiet a profound, chilling mystery. Perhaps the reason for the cosmic silence isn't their absence or their choice to hide, but our limited perception. Alien civilizations might simply be too truly alien for us to recognize, existing in forms or utilizing technologies fundamentally unlike our own. Our search for technosignatures assumes a certain type of technological development: radio, lasers, energy harvesting. But what if truly advanced civilizations have transcended these, using physics or energy manipulations beyond our current comprehension? Their biology and consciousness might be so radically different from ours that we wouldn't even recognize them as life or intelligence. They might not be carbon-based or exist as distributed intelligences across a planetary network or even stellar objects. Concepts like post-biological intelligence, where consciousness is uploaded or transitioned into advanced computing systems, could mean they operate at speeds or scales beyond human perception, processing information unrecognizably. Their communication methods could be entirely non-electromagnetic. They might use neutrinos, gravitational waves, quantum entanglement, or even methods that manipulate spacetime itself, which we currently have no way of detecting or decoding. Civilization might not leave any waste heat or conventional signals. Perhaps they are incredibly efficient, consuming only what they need, or have mastered energy recycling perfectly, leaving no detectable technosignatures as we understand them. They might have evolved beyond the need for physical structures, existing as pure energy or information patterns. Such beings would leave no physical trace and would be completely invisible to our current scientific instruments. The very concepts we use to define civilization and technology are anthropocentric. We project our own evolutionary path and technological trajectory onto the universe, potentially blinding us to truly alien forms of existence. This implies that the true challenge isn't just about building bigger telescopes, but expanding our conceptual framework of what life and intelligence can be. It requires a transformative shift in our understanding of the universe. If aliens are too alien to recognize, the cosmic silence becomes the sound of our own limitations. It's not a silence of absence, but a silence of inaudibility, a universe teeming with life that speaks in frequencies we simply cannot yet perceive, making the silence a mirror of our own undeveloped senses. Even if intelligent life is common, the sheer scales of time and distance in the universe pose enormous barriers to successful contact. The cosmos itself is a vast, silent expanse, ensuring that any forms of communication occur across staggering gulfs. Distances are measured in light years, meaning signals take years, decades, centuries, or millennia to traverse interstellar space. A simple hello and reply could span a human lifetime, frustrating any attempt at meaningful conversation. Consider the nearest star system, Alpha Centauri, just over 4 light-years away. A round-trip message would take more than 8 years. For a civilization 100 light-years away, it's a 200-year conversation. This makes real-time dialogue impossible. The cosmic haystack problem further complicates things. Imagine trying to find a specific needle in an infinite, ever-changing haystack. We don't know where to look in the galaxy, at what frequency they'd transmit, or when they might be transmitting. Civilizations might rise and fall within the time it takes for a signal to cross the vast emptiness between stars. A message might arrive only to find a silent ruin, or a response might be sent to a star system that no longer harbors an active civilization. Our own technological window might be too brief. Humanity has only had radio telescopes capable of detecting interstellar signals for a few decades. In cosmic terms, this is less than a blink of an eye. Active civilizations might exist in different epochs. Perhaps 1 million years ago, the Milky Way was teeming with advanced societies, but they are all gone now, leaving only faint, undetectable echoes, or their signals have long passed us by. Our current search strategies are limited to our immediate galactic neighborhood. We haven't even fully surveyed our own Milky Way, let alone the billions of other galaxies, each potentially teeming with its own silent worlds. The energy required to send a detectable signal across vast interstellar distances is enormous, possibly more than a civilization is willing or able to expend continuously for long periods, explaining why there are no persistent beacons. The problem of scale ensures the universe's pervasive silence. The enormous distances and immense timescales mean that even a cosmically common phenomenon, like intelligent life, might effectively remain isolated and unheard, each within its own profound, silent bubble.